perfluorinated chemicals and phenolic chemicals as well. And of course, we see about the antibiotics. We see the antibiotic itself, but also we're concerned about the antibiotic resistant gene. In my view, is kind of organic pollutants. Of course, it's a gene, and also as we all suffering now is a SARS-CoV-2 virus, and we see maybe we could in the future we could do something with our passive sampling. We're concerned about these micropollutants or microorganic pollutants because they can be persistent in our environment, like this figure shows back to 2016. Most of them are is longer than 120 days in our environment. And we concerned because also these chemicals cannot be treated or by our currently designed wastewater treatment plant. So that's why they are because they are not really designed for these micropollutants. That's some new design might be and a way to really remove or consider removing these micropollutants. And also there are large quantity of these chemicals, and I can show you so many different kind of pollutants can enter into our environment. And the thing is, these chemicals might have some adverse effect. And like these papers shows, there are many of the kind of papers or studies on this topic. And also, thing is the risk of these chemicals, particularly the mixture, because all these chemicals are into the environment as mixtures. So the mixtures effect is uncertainty, which is more concerned by ourselves. And also, this number of chemicals are always growing. That's another thing we need to think about. Talk about some action in China in the last few years. Since all of this, the old pollutant like the nutrients or heavy metals have been relatively well controlled. And then the Chinese government and scientists from China start to think about the emerging organic chemicals. Back to 2 years ago, in our the 15th, in our 14th 5-year plan, and then we started to think about this emerging pollutant, and then they particularly give some examples like the PFAS, the EDCs, antibiotics, and also the microplastics. And last year, our Ministry of Eco-Environment already mentioned that we need a plan to monitor and control these emerging pollutants, and they issued this action plan for controlling emerging contaminants. It's an open draft comment. And this early this year, actually in May, our state council issued the action plan. In this action plan, the key word or something we particularly want to do is a screening, assess, control, ban, reduce, and treatment or treat of these emerging organic pollutants. So in this plan, the first step actually is to know what are in our chemicals and what their level in our environment. So the first step we should monitoring their occurrence and in our different metrics of the environment, in the water, soil, air, even. Usually there are 3 different options to do this kind of monitoring, particularly for the sampling purpose. Is the first one, or very common, very mostly used one, is active sampling. as probably most of you knows that when we do the initial research or kind of initial understanding of the level or occurrence of the chemicals, we grab water from the river or lakes, which we call it a grab sampling. It is most commonly used in the literature, and also another more proper sampling method is called it automatic sampling, which use the automatic sampler like this one. Basically is a pump, programmed pump to sampling water from an environment, which is the gold standard for the proper environmental monitoring, particularly for the old like heavy metals or nutrients. They use this kind of we call it a standard sampling approach. And another big group approach for monitoring is biota. Like we could use mussels, fish to monitoring some chemicals that they accumulated in their bodies. But this sampler might be, is because they are biological. They are varying in the environment or individuals, so they might give big uncertainty. And another or the last kind of approach is a passive sampling. In fact, passive sampling is not new. Back to 2013, the European Union Water Frame Directive, they mentioned that that some passive sampling should be used or tested in the future for this kind of environmental monitoring. Last 2 years ago, in a science paper, they also mentioned that the state-of-art sampling extraction method is a passive sampling. They kind of argue that this sampling approach is more powerful. Yeah. So what is the passive sampling technique? In fact, so the passive sampling is really based on the free diffuse of analyze or your target chemicals from an environment to your medium, to your designed sampler, or to our to the bounding phase or bounding area, bounding layers that which track your chemicals when they diffuse from outside, right? The advantage of this passive sampling is that firstly is in situ, is the active sampling, or we sometimes we call it ex situ. So and second is time, labor, or cost effective. I'll show you later with our own data on this point. And also it can give us the time weighted average concentration, which is more representative, I think, because sometimes if we use the graph sampling, as this figure shows, sometimes we might miss the peak. Sometimes we, so it gives you a kind of a snapshot of the concentration in that time and at that point. The passive sampling for water, passive water sampling for organics is not, as I said, is not new. Back to 1990s, there are already some passive sampling like SPMD or SPME. Particularly these chemicals, this sample is particularly used for POX, for the very hydrophobic chemicals. And the other part of this kind of sample is on the right side of this slides, is for the particularly for the emerging or polar organic chemicals, which is more water soluble. And at the very beginning, there's a chemical which also used for this particular group of chemicals, and later on there is a process as you can see, all these samples look like quite similar, but I'll tell you later what's the key difference later. Before that, I would introduce you the diffusive gradient in thin film, the DGT technique. So this is how DGT looks like. It consists of a base and a cap, and between them, there are three layers. From the very bottom is the bonding layer, which we use it to trap the chemicals after diffuse from outside. And the middle layer is a diffusive layer, or diffusive gel, plus a filter. Outside the layer is a filter, which can protect from particles or some microbials into the sampler. This is a structure. So the basic principle of this DGT is based on the fixed first law of diffusive, which is equation 1. F is the fluxes, D is the diffusive coefficient of chemicals through the diffusive layer, and the CB here is the concentration in outside environment, like water concentration, and the CI is the concentration in the interface of the bonding gel and the diffusive gel. And delta G is the thickness of the diffusive gel plus the filter thickness. And delta G, the small delta, is the thickness of the diffusive bonding layer, which is always varying, depends on the water movement, depends on the water velocity, on the water flow rate. In fact, if the water flows very fast, then this dBl will be very small. And sometimes, if there's no water movement at all, that might be very big. I'll show you later from our own data. So the key things compared to other sample is here. We have the delta G, the diffusive layer thickness is much higher than the diffusive bonding layer. So that's the key, which we could use this layer to control the sampling rate. Because if we don't have this diffusive control layer, like the process of chemical, then the dBl will control the sampling process. So, but this layer is always varying, depending on the water movement. So that's the key for the DGT. So from this equation 1 and 2, we can get equation 3, and by rearrangement, we can get equation 4, which we could calculate the C concentration in the environment. As you can see in this equation, M is the mass of your target chemicals absorbed on the resin gel, and delta is the thickness of the diffusive layer. D is the diffusive coefficient, of which we could measure independently, or we could predict through our models. In fact, as mentioned, I will tell you later. And A is the exposure area of this window on the cap. And T is the diffusive time. It's a deployment time in the river, in the environment. So if we know the mass of your chemicals on the bonding gel, then, and if we have this D value, then we could calculate out the CD, means the concentration in the water. So that's the background of this sampler. So this DGT sampler was invented back to 1990s, and the first publication is on Nature in 1994. Hao Zhang is one of my supervisor. And since then, there are quite a lot of research or applications, but mainly focused on the heavy metals or nutrients, basically the inorganic chemicals. Because this sample has so many advantages and so many applications, so many kind of series already, Then when I did my PhD to Lancaster back to 2010, and our idea is if this sample is so good, then why not for organic chemicals? So that's kind of my PhD topic or PhD direction. And then that's my mission for that. So in order to kind of demonstrate that this sample can be used for organic chemicals, we did this test. We use antibiotic, one of the antibiotic as SMX as a kind of a model chemical, and also we use a new bonding phase, like we use test X8018 as a new receiving phase or bonding phase to trap the chemicals, the antibiotic chemicals, and we demonstrated that it can be, can be follow this equation as well. It's no problem, and we also test the water flow rate effect on the sampling on the sampling measurement. As we can see, if there's no movement at all, we can only report the kind of a half of the real concentration in the water. And then if there is a bit water movement, like of course we use a stirring rate there, and then it will be enough to quantify the chemicals correctly in the water. And this kind of proof of concept, this DGT idea, and then we went to the field to test in a real environment, and also following that, there are so many scientists from all over the world that tried for different chemicals. And so in the last few slides, I will show you this kind of story on this line. So this is our first real field test in a very kind of a very harsh environment. We deployed this our sample in the influent of and the effluent of the wastewater treatment plant, and we validate this sample by comparing with the active sampling, like the standard one, the automatic sampling, and also the grab sampling. And this is the key result. And our result shows that the OGGT result is comparable with the automatic sampler, and both better than the grab sample. As you can see, the red bars is for the grab sampling, which we do the kind of mimic the commonly used sampling approach. We take one sample per day and directly to compare with our GT and the automatic sampling, and we can see the very high uncertainty for this kind of method. And also we tested our the idea about the DBL in the wastewater treatment plant as well. By doing this, we use a varying thickness of the diffusive layer in DGT, and I deployed them at the same time. And then through this equation, we could calculate out the diffusive layer thickness, diffusive boundary layer thickness, which is delta. And if we ignore this kind of diffusive layer, we calculate out that it can only underestimate about 25 of the real concentration when we use a standard diffusive gel, like 0.8 millimeter ones. Of course, if we use higher, thicker one, like 1 millimeter, they will further reduce this uncertainty. And we also did the comparison between these samplers in terms of their cost or time or other consumable cost, and we found out that this passive sampling approach is really can save a lot of time and also a lot of consumables. So we call it a greener sampling approach. In the last few slides, I'll show you what's the recent advances in this organic DGT area. Particularly, we try to start to use our state-of-the-art technique like the 3D printing and also the machine learning techniques. Since our first two paper published, there are so many other publications followed and focused on tested other chemicals like phenols, bisphenols, pesticide, illicit drug, even EDCs, personal care, blah blah, and these chemicals until now there's about this is from last year, from last 2 months. I think now it's about 200 chemicals published on the DGT. Basically, they span a very large range of chemical space, like from the very small chemicals to very big chemicals. And if we look at the hydrophobic, based on the QW, is also a very large range. That's the chemical space. From our own, since I am back to China, we also looking for some new chemicals like this one, the potential which called potential persistent, mobile, and toxic chemicals. And this chemical is established the biggest chemical currently, and first reported in Germany, and then we think, oh, if we could find it in China with our sampler, with our DGT sampler, and yes, we did. We developed this sampler and found them in the wastewater treatment plant, and also later on, we did some application to the river, and also we applied this sampler to other TMT like the melamines, which is probably you guys know, it's a very big problem last in maybe 10 years ago in China, because they add this in powdered milk, and also, but actually these chemicals, it also is kind of a material for some plastics. So we try to see how, if we could find them in an environment. And the answer is yes, we could find them, and we could use our DGT sampler. And others, like we also did after the Lancaster one, we used this sampler for the Chinese wastewater treatment plant, and also for the rivers in Guangzhou for EDCs for a long time monitoring. Also, at the same time, we compared with the chemical sampler, and also we did, as I mentioned, this diffusive coefficient is really a kind of a chemical dependent parameter. So we have been thinking if we could use the QSA model, the quantitative structure property relationship model, to predict this D values, and if so, then in the future, particularly for some non-targeted screening studies, if we could predict the D value, then we could directly use the DGT for a non-targeted screening. So that's kind of a background idea behind this this publication. So we did a study with the quantum chemical descriptors, and we use the multilinear regression models. We particularly use these QSA-in tools, is a free available tools, and we found yes, it seems good enough for this particularly purpose. And of course, we currently if we have more measured D values, we could even do more better of this modeling, which we have been doing now with our machine learning approach. So this is the one. So we try to use this kind of open source, open available, free available software like the pedal, which we could get all the molecular descriptors, 2D or 3D, and then we use the traditional machine learning models, and also the artificial neural network ones. And this is unpublished data, but until now it seems quite good, quite promising, and particularly when we input more our D values from the literature. And in another kind of direction we have been working on is before this study, we are actually using the bonding layer, the bonding gel, kind of have no selectivity. So it means you can sample any chemicals from the environment if your bonding gel can absorb your chemical. But from this one, we think, oh, if we could use the kind of more selective, high selective the resins to particularly focus on a specific group of chemicals. So this kind of the idea that we use a molecular imprinted polymer as our bonding phase in the DGT, and we found that yes, it can work quite well. And also we try to use this molecular imprinted sample DGT to understand the effect of the kind of water parameters like the DOM and pH or ionic strengths. We found out that they can have some interaction effect on the sampling or maybe other environmental processes. And also, this is not from our study, but it's a good one to kind of link the DGT measurement to the bioaccumulation, or even maybe later for the toxicity. So these guys use the DGT sampler and the zebrafish to see if they can have a good correlationship between the sampler and the biota. So they found a good relationship. So that means they can kind of a surrogate method with the DGT for bioaccumulation in the future, which is quite promising. And recently we also did, the microplastic area. We have been thinking if we could use or how to use this our DGT for understand the chemical interaction with the microplastic. And we did this kind of study with triclosan as an example, and we use PE and PS as a model microplastic. We found that there is also a pH and ionic strength interaction effect on the desorption or the absorption process of the triclosan in the microplastics. So this study hasn't been published. We have been revising our manuscript. Will be submitted later. And for this study, we have because a lot of other guys from like particularly the POSIS guys, they have a very big sampling area, but our sampler, I'm not sure if you guys know, is that the disc one, this DGT is a very small one. The diameter is only about 2.5 centimeter. So they have been criticized that this sample is too small, or too less sensitive in monitoring organic chemicals in the environment. That's why we have been thinking how to kind of enlarge. Although a long time ago, in our first paper, not the second paper, the ESNI paper, we already mentioned that if people think that that's a sensitivity problem, then we can pool the DT, several DT together to increase the sensitivity. But of course, that might increase the cost because you need to buy more DGT, right? So based on that this kind of idea, we have been thinking how we could use this larger DGT. Of course, we use 3D printing printer to can print bigger DGT like the 47 millimeter ones, like the chemical. And also, in fact, we have in the DGT family, we have the Prof one, because the length of this is about 18 centimeter. So it has a higher, much bigger the sampling area, which could increase the sensitivity of this sampler. So that's kind of our trials with this DGT probe for PFAS in of course, we here use the water and sediment as a kind of a environmental media, and that kind of one purpose. Another purpose that we want to show people that with this sampler, we could insert this probe half in the water phase and half in the sediment phase. Then we could kind of look at the transfer between the water and the sediment, kind of a dynamic change. So this kind of the main key result from this recently published paper, and when we show that, that's quite promising as well. Okay, give it a summary. So from our study, or of course from other together with other people's study, we think this sample is cost-effective to monitor the time-weighted average concentration, which is more representative in our opinion, particularly for this polar emerging organic pollutants. And passive sampling, particularly the DGT, is very promising for monitoring these chemicals. And we also have been talking to people that this DGT or other passive, of course, is not only an environmental monitoring tool, but also a scientific technique, and it is permission for understanding the phase behavior of chemicals in the environment, in the water, sediment, and even in soil, and particularly on the interface between two different metrics like water, sediment, or water, soil. Give you some perspective in the future. So for the environmental monitoring, like the WFD, they already mentioned that, and I think they already started a bit on this passive sampling technique. And also in China, I think we have tried to tell the scientists or the government that this sampling is useful. And so for this kind of purpose, we could do, of course, target analysis of these emerging chemicals. And also in the future, actually, we are already started with, we have 2 students who have been working on this direction. We try to do the kind of a non-target screening study to with our high resolution MS mass spectrometry, and of course we have in aid of the machine learning to identify unknowns in the environment. Particularly if we have, particularly we are trying to use the probe one because it has a larger sample rate. And of course, recently we saw some papers also on some environmental DNA. Particularly some people use passive sampler, other kind of passive sampler for this SARS-CoV-2. There's few people already. So in the future, we might also try this for this kind of a DNA or virus purpose. And I have already asked one of my students to start to try a few bits of testing. And another area, as I just mentioned in the last slide, we could use this sampler to deeply understand the environmental process in situ. So the key is in situ, like the sorption, desorption, or release in the sediment or soil. And also we could use this sampler to understand the complex of this coexisting substance like heavy metals or other DUM or SPM. Suspended particle matter, their interactions, and of course the water sediment exchange, particularly in the river system, right? And another Another area would be, as I mentioned, the bioavailability or bioaccumulation. If we could use, of course, for the realistic drugs, they already demonstrated that. But for other chemicals or processes, we might also need can use DT. For this study, for this kind of study, we already tested antibiotics in soil with DDT and also with some plants to compare with these two samples, which is the initial results sounds quite nice. And of course, besides this, and the DDT, in the future, we might also use the DDT measurement with some other bioassays like toxicity studies, and we can use this for effective directly analysis. So that's kind of the future. Where part of this, we already in my own group here, we already started to try. Okay, closement, some guys, some supervisors, co-authors, my postdoc students, and also very thankful to the founders from every China, UK, and Stockholm as well. Okay, that's my talk for today. Thank you very much for your attention. And if you have any questions or even collaboration in the future, I'm very happy.
Thank you very much, Professor Chen. I hope you all enjoy this amazing presentation. I have learned, personally, I have learned a lot about how DGT can be used as a powerful environmental monitoring tool. So now let's go to the question. Okay, so the first question is from Amy. Hi, Dr. Chen, do you think that passive sampling can eliminate the need of analytical extraction plus enrichment steps together, such as the SPE?
Say it again, sorry. I did it with you. I'm not quite with you, actually.
Yeah, so I will repeat the question. Yeah. Do you think that passive sampling can eliminate the need of analytical extraction plus enrichment steps together?
This means combined with SPME, or what's the question actually?
So I think the participant actually means that if we are using the passive sampling method, can we just skip the extraction or skip the SPE step and directly go for instrumentation analysis?
This means the kind of a pre-treatment, right?
Yes, yes.
Exactly. It depends on your research purpose, right? If we could use this like a water sampling or soil sampling, if your purpose is kind of test it the new approach, it's better to kind of compare with the traditional ones that we have been always been doing to test the new sampler, new techniques. So if somebody already tested that, yeah, that's kind of replace or replace the pretreatment, then that would be good. But if it's kind of a new area or new chemicals, it might be required some testing before directly use. Did I answer the question?
Yes, Prof. So thank you for your answer. So we have a second, yeah, we have two questions from Mo Asmi. Yeah. So the first one is, what adsorb material that usually used for DGT preparation? I mean, what type of material are usually used for this method?
Okay, So the material for DGT, right? And basically, we for the inorganic one, so they use polyacrylamide gels, hydrogels, and for the initially we also tested for the polyacrylamide gels, and for the DGT, because we need for the organic chemical, we need to make sure that the chemicals cannot be absorbed by our material, like the filter membrane and the diffusive layer. So we tested the agarose-based gel, and also different kind of material of filters to make sure these chemicals cannot be absorbed significantly by the filter and bonding gel. So for organic chemicals, most of the studies have been using the agarose hydrogel. And of course, we have also started to test some other polyacrylamide gels, which can, if they have a limited absorption of your target chemical, that should be okay. But for the filters, there are so many filter membranes we could choose, like PES or PTFE or nylon. There are so many kind of filters we can choose, but the key is we need to test if they can absorb your chemical. If they can absorb your chemical significantly, then we need to try another different. So this kind of material we use. And for the housing, for the DT housing, we use ABS plastic. Of course, now with our 3D printing, we use the degradable plastic, PLA plastic for to print out our DGT holder. Did I answer the question?
Yes, I think you have partially answered the second question. Is the DGT a multifunctional or selective diffusion gel?
Particularly for the diffusive gel?
Yeah, is this is like a multifunctional, means it can target a wide range of chemicals, or it's only very selective?
For the diffusive gel, it's not really selective. It can let any chemical, even metal ions or nutrients, pass into the sampler, into the bonding gel. So for the diffusive gel, there's no selective. Maybe in the future we could design, but I don't know how. Maybe some people can, some guys from chemistry can design this kind of a diffusive gel. But currently we don't have a selective diffusive gel. But we do have as I mentioned, we do have the selective bonding gels with the MIP polymer.
Okay, so the next question is, how do you deal with the selectivity issue for certain contaminants that have similar log KOW during the passive sampling?
Wow, that's a very good question. Actually, as I mentioned, that even with a selective bonding gel, it's difficult to kind of really select the particular chemical. It's really for the MIPs, for example, it's really sample the chemical with very similar chemical structure. Kind of a group of chemicals. If the chemical has a very similar structure, a part of the structure, then it can select or bond the chemicals. But for the selectivity, actually, we kind of not that keen on that, particularly for a wide range of chemicals, and we could detect them, or we could detect by selectively detect them by the instrument, like the LCMS. Particularly, we use LCMS to separate them and detect them, but not by the bonding gels, except the MIP. Even the MIP, is kind of sampling a group of chemicals, very similar chemical with very similar chemical structure. So talking about the QW kind of cutting edge, it's difficult to see what kind of QW range we can sample in, but because it depends on the filter, outside the filter membrane. If the filter membrane can absorb particularly very hydrophobic chemicals like QW more than a log QW more than 8 or even higher, and it can't travel or pass through the filter. It will be trapped by the filter membrane, so it cannot travel further into the bonding gel. So with that, so that's why I said we need to test the proper filter membrane in order to kind of let the chemicals, your target chemicals, diffuse through the filter membrane and also the diffuser gel into the bonding gel. Is that okay?
All right, thanks, Prof. So I think we have a last question of today is from Amani. Have you done any research related to the samples containing household products such as detergent or surfactant?
Estrogen or surfactant? Say that again, Joo Hui. I'm not quite.
Have you done any research related to the samples containing household products such as detergent or surfactant with your passive sampling technique?
Contaminated by these two kind of chemicals?
Yeah, focusing on the household waste, basically. So the example of the household waste that I was given was detergent and surfactant.
Is this question about the kind of compete with the estrogen or surfactant, or is that what he or her means?
I think the question is actually, the participant is actually asking, is it possible to apply this method to sample like household waste, like the wastewater from household product?
Okay.
Because we are doing the laundries, we are using the shampoos, and maybe is it possible to capture this chemical as well?
Okay. So for the waste, kind of solid waste, or
I think it refers to a liquid waste from household.
Yeah. For this kind of chemicals, definitely yes, because we already tested it for some estrogens, some household chemicals ingredient, like from our shampoo, other chemicals, and for the liquid ones, definitely it's okay, but it depends on the real environment. If it's a very harsh environment, like the boil water. Of course, if it's from a household, like the influence of the wastewater treatment plant, that should be okay. But if it's very harsh, like even very too much solid, then it might be, it might be a problem, like clog your sampling pass. But that should be okay, yeah, because we use the sampler for sediment and a soil, and so it's kind of a different area to understand the process. But if it's purely for liquid, that's definitely okay. But if it's a solid, then we need to think about the kind of a desorption process, and it's kind of another advantage of using DT for more complex environment. So the simple answer is yes. We have been using for household chemicals ingredient, but for the surfactant, in fact, the PFAS is kind of surfactant, so it should be okay. But we haven't really particularly tried DDT for the commonly surfactant from household. But from the PFAS study, I think it should be okay for these chemicals as well.
Yes, we have another question from Dr. Bosliza. Can we use passive sampling for inorganic sample as well?
For which kind of sample?
For inorganic sample.
Inorganic samples. Inorganic samples. What's that means? Inorganic chemicals or?
Yeah, I think yes, it refers to the inorganic chemicals. Yes.
Yeah. This DDT actually was developed for inorganic chemicals at the first initially developed for heavy metals and nutrients. So it's no problem at all. There's the first paper is published on Nature is about some nutrient or heavy metal ions. So it's my PhD area that started to use this sampler for organics. It was initially used for inorganic chemicals because there's so many advantages compared with other passive sampler for organic chemical. Then we start to kind of extend this sampler for organic chemicals. So yes, definitely yes.
Yes, I think we have finished all the questions. Thank you, Prof. Chen, for answering all the questions and for a very great presentation. It was an honor to have you with us today. So to all the participants, please fill in the attendance form in order to get your e-certificate, but this is only limited to analyst member. And please also help us to fill the survey form so that we can improve the webinar better. And now let's take a photo together with our speaker. So please turn on your camera and we will have the Asmi maybe to help us to.
Hello guys.
Assalamualaikum. Good morning all. So can you help us to open the camera so that we can take a picture together with the speaker? Wait, I'm waiting for the other to open.
Are all you guys from Malaysia?
Oh, mostly from the Malaysia.
Great.
Okay. 1, 2, 3. Ambil gambar tak? Abang hilang. Okay. Gambar. Okay. Thank you very much.
Thank you guys.
Thank you very much for your help.
No problem.
For your sharing. Besides that, Prof, after this, hopefully we can connect together and most of them maybe from the others researcher from the Malaysia can collaborate with you for the next future.
Yeah, of course. Yes, of course. We are always open. As I said, I mentioned Tay Joo Hui. So we are always open. And we have quite a good instrument set up here. Quite a full range, GCMS or LCMS or Q12, GC Q12. So you're always open. You're always welcome to come if you guys can in the future.
Sure, Prof.
Okay. for
Okay,
today.
thank you very much, Prof.
Thank you.
See you
Bye.
again.
See
Bye.
you somewhere.
See you, Prof. Bye bye.